Okay, in this lecture video, we're going to talk about how line surface integrals relate to the coordinate system that you're using and how they change. All right, so let's take a look at this. Let's just start out with the Cartesian coordinate system, since that's the simplest, and we're going to draw it in this fashion. I'm going to have the x-axis here, the y-axis here, and the z-axis there. Notice x hat cross y hat equals z hat, which is required for any right-handed coordinate system that we're using. This is called Cartesian. All right, so what would we substitute into a line integral if we're integrating in Cartesian coordinates? So that really depends on where your line integral is going. For example, let's consider possibility A, that we have a line integral that's sort of progressing in this direction. If that's the case, then the line integral for A, that small vector dl, we'd replace it with a dx in the x direction. All right, let's consider another possibility where we've got a small vector that's pointed in the y direction. So we're basically integrating along the y direction, in which case, for this, the dl vector that goes in the line integral would be dy times y hat, right? Since it has a small length, dy, and it is pointed in the y direction. And the same for c. You can probably immediately see that this will be dl. You substitute with dz in the z direction. All right, but what about, for example, if we have a line that is oriented this way, right? At a 45-degree angle between the z and the y-axis. Let's call that d. What would we substitute in that case for our dl vector? Right? In that case, dl is basically going to be a small vector, but we're going to have to divide it up equally between dz and dy. So this would be dz divided by square root of 2 in the z direction plus dy divided by the square root of 2 in the y direction. Right? We're basically taking this to be a 45-degree right triangle, in which case each of the components is 1 over square root of 2 to get a hypotenuse of 1. All right, so that's for Cartesian, and this works for any direction as well that you might point it. But the magnitude of dl basically has to be a d something, right? It has to have effectively 1 unit of differential length. Right, for surface integrals, let's say we have a surface integral that is oriented in the xy plane. Right, so for that, we would have a substitution for this ds vector, right, into a surface integral. So these equations here are for lines, and these are for surface integrals. Right, ds in this case would be, first of all, it'd be pointed in the z direction. Could be positive, could be negative, but it's definitely in the z direction because the vector itself is pointed through the surface. But the surface area of that vector is going to be in the xy plane. And so we're going to write this as a dx times dy. So it has units of area. And you can do the same thing if you have it oriented. I'll just do one of the 2 remaining possibilities. In this case, we would substitute ds equals dx dz, and would be oriented in the y direction. All right, so that's the surface integral. And then for volume integrals, if we have a differential volume that we're going to substitute, then that's just going to be the product of the 3 components, dx, dy, and dz. So it has units of volume. All right, so that's Cartesian. The cylindrical coordinates are going to work a little bit differently. Because of the fact that if I draw this cylindrical coordinate system right here, and then we consider a small angle here, and we'll call that d phi, then the actual length of this segment that's on the arc here, the length of this segment is going to be d phi times rho, where rho is this radius, the radius of the circle outwards from the z-axis. This is the z-axis here. So for that reason, the ds vector, if it has, let's say, a d phi times dz, also needs to have a rho in it, because again, the same slice of angle corresponds to a bigger and bigger distance as you multiply for larger and larger values of rho, of that radius. All right. The rest of the formulas you can find in the notes, so I'm not going to write them all down since they're all self-explanatory. But let me just briefly now talk about spherical coordinate system before we conclude. All right, so here is our vector r in cylindrical coordinate system, and here is the line that goes to the North Pole and the South Pole. So this angle here, downwards from the North Pole, is what we call theta, and this vector right here is r hat. This vector that sort of points toward the South Pole on the surface of the sphere is theta hat, and it's kind of hard to see, but there is a vector that kind of points eastward, and that will be the phi hat direction. All right, so taking these coordinates, then for the volume integral dv, it's going to work out to be r squared times sine of theta times dr times d theta times d phi. You'll notice the units have to work out, right? You've got a meter squared from the r squared, and you've got a meter from the dr. So that's an r cubed. So, sorry, that's a meter cubed, as it should be. The theta and phi don't have any units with them because they're just radians. So that's the dv. The dA, or the ds vector, will depend on where your surface is located. So if it's sort of a patch on the surface of a sphere, then that would be r squared times d phi times sine theta times d theta. Basically, it's the same as the volume, except remove the dr, right? And this would be a patch on the surface of the sphere. And again, there's two other ways to define the a ds vector, depending on whether it's a patch along the surface, whether it's a patch that is in the r theta plane, or it could also be in the r phi plane. So there are two other possibilities, and again, you can see those in the notes. So anyways, the point of this is just to show you the way you might set up and substitute into line or surface integrals. The important part for real life problems is going to be learning to set it up, not necessarily how to analytically solve double or triple integrals. As we're going to talk about, there will be sort of numerical ways to solve this problem that we're going to learn to understand. But at least understand how these work and how you adapt your integral to different coordinate systems is important as we go forward.